Hello. Yes, it's on. So hello everybody, welcome to my session on Groovy, especially Groovy 2.0. We'll cover also a bit of the features of Groovy 1.8, a bit of both, but quite some time on 2.0. Just a quick few words about me. I'm Guillaume Laforge. I'm the project lead of Groovy, and I'm working for SpringSource, division of VMware. I've been working on Groovy for the past 9 years, quite a bit of time. Groovy is quite mature, obviously. I initiated the creation of the Grails framework, created Gaelic framework, that's a small toolkit for Google App Engine. I co-authored a few chapters of that book, and if you want to know more about me or follow me, etc., here are some links you might be interested in. That's all. So the agenda, 2 big parts, some of the key features of Groovy 1.8 which are interesting. But first, perhaps I should ask the question, who knows Groovy, who's, played with it or is using it, etc.? Yeah, okay, the majority. So perhaps I'll go a bit quicker on the Groovy 1.8 features. Who's using Groovy 1.8, actually? Okay, and who's already using Groovy 2.0? Okay. Good. So let's say 2/3 on 1.8 and 1/3 on 2.0. Okay, so some key features of Groovy 1.8, and then we'll cover all the new features in Groovy 2.0. So let's start with Groovy 1.8. One of my favorite features of Groovy 1.8. So Groovy 1.8 was released already a year ago. It's a small syntax enhancement which allows us to create DSLs, domain-specific languages, which are quite readable and more readable, looking like pretty much like English or French or German sentences. It's a syntax improvement where you can drop dots and parents so that it really looks like plain English or whatever language you're using. So let me show you an example right away. For example, something like pull request on GitHub. It's actually valid Groovy code. It wasn't the case before with Groovy 1.7 and older versions. And it's an alternation of method names. So pull and on are actually method names, whereas request and GitHub are parameters. You can also have several parameters separated by commas, or you can have named parameters with key name, colon, value. And this is actually equivalent to calling this equivalent to pull request. That's the first parameter of the pull method. This call is returning some object on which we are able to call the on method, which takes GitHub as a parameter. So this is the basic principle. And let me show you some other examples of what you can write with that little syntax enhancement. So it's totally equivalent. The two notations, I add the parents and dots back, are totally equivalent. So that's, in terms of when you run that, it's really the same behavior. It's really just a syntax sugar, if you will. Speaking of sugar, take coffee with sugar, milk, and liquor. It's pretty much like plain English, and it reads very well. You can use named arguments, and I'll put the parents and dots after. So I'm just showing the examples first, and you can try guessing where the dots and parents are. Named arguments, check that margarita tastes good, and the colon kind of separates both parts of the sentence. You can also use closures. For example, if you want to create your own control structures, like if you're doing BDD, behavior-driven development, using some BDD toolkit or framework, you might be familiar with given, when, then, and you can use closures as if you were creating your own control structures to define when given something, when something happened, then, and putting that in the body of those closures. There's one case where you actually need parents. It's when a method in the chain of calls requires doesn't take any argument. So when there are 0 arguments, you'll have to use the parents to disambiguate. And you can so far you saw one method and some parameters, one method, some parameter. But you can it's an even number of the same an even number, let's say, of method names and arguments. But you can also have an odd number with take3, which returns something, and you can call cookies, which is a property on the return value. Let me put the parents back. For the first example, you can see that I can use several arguments for the with goal. So there's a comma to separate both arguments. In this case, it's interesting because visually, you see the colon, which kind of separates, check that, and Margarita tastes good. But the actual named parameters is that colon Margarita. For closures, it's quite simple. You just put the parents around the curly braces. And this one is also quite straightforward. And as I said a minute ago, when you've got an odd number of terms, it's like calling a property, the property notation, on the return value of take3. Okay, so that allows us to create some very interesting and very readable domain-specific languages, which is an area where Groovy shines. Another little novelty is that in the Groovy distribution, when you download the zip distribution of Groovy, or if you use the Windows installer if you're on Windows, we also bundle Jeepers. Jeepers is our Swiss Army knife for everything concurrent, parallelism, concurrency, and I forget one. So everything parallel, etc. It's taken care of by that library, providing actors, some simplifications around the fork join model, map filter reduce, etc. of Java util concurrent, and some other things like data flow, which is a pretty interesting concept. Parallel arrays, STM, that's software transactional memory, etc. And what's interesting as well with that library, Jeepers, is that although it's very nice to use with Groovy, it's featuring also a Java API that you can use from Java. So you can use and leverage all those concurrency, parallelism concepts from Java if you don't want to use Groovy directly. So it's quite interesting. Closures, well, Groovy's had closures for the past 9 years, so we didn't wait for JDK 8 to get closures or lambdas. Closures are a really nice cornerstone of the Groovy language, and it's used throughout the APIs in Groovy. Well, it's used in the APIs for things like, like adding a functional flavor to the language, because you can write functional algorithms, describe your algorithms with a functional, in a functional way, and we keep on adding some features to further give you some further possibilities in terms of functional composition, etc. I'll just cover regarding the functional flavor, I'll just cover the memoization function and another enhancement, which is about the ability to use closures as annotation parameters. So let's start with that one. I'm trying to do a very small example here to implement design by contract, like you can have in languages like IFO, etc. I want to define an invariant. I could define a precondition, postcondition, and that kind of things. So I'm going to use an annotation. So I create an annotation. That's the first 4 lines. Although we're going to pass closures as parameters, the JVM won't allow us to say, okay, the value parameter of that annotation is a closure, so we have to encode and somehow cheat to tell the JVM that it's a closure that we actually encode in the form of a class. Then I'm able to annotate my distance class with that annotation. And you notice that I pass a closure as parameter of my annotation. And then how am I going to use it? So you could imagine a proper framework doing that kind of job, but here I'm doing things manually, obviously. I instantiate a distance, then I retrieve the annotation associated with that class. I get the value, which is actually the closure class, which I'm instantiating. So I instantiate a closure That's what I do with new instance, and I'm passing some parameters to the closure constructor. And then I'm able to call check, which is check the variable that we just created is the closure instance. And I'm calling that closure. I'm passing the actual distance to that closure. And that way I'm able to check that the number for that distance is actually positive. So it's quite nice to be able to define annotations with closure parameters. For example, if you're a framework author or framework developer, there are cases where you could want to define your own validation constraints, your own routing rules, etc. So you can put some actual logic instead of pointing at a class or pointing at a string. You can point at a closure and real code inside that closure that you pass to as a parameter to your annotation. So this is quite interesting for framework authors. And obviously, since it's a closure, you can put any amount of code inside that closure. So avoid putting too much code in annotations. That would be a kind of an anti-pattern, obviously. And so if you're interested in design by contract, there's actually a library called G-Contracts, which provide the full-scale, full-blown design by contract patterns for Groovy through that mechanisms of closure annotation parameters. So G-Contracts, just Google that, and you're able to easily add that to your project. So it provides, pre, post conditions, invariants. It works across hierarchies of classes and so on. So it's quite powerful. Closure memoization. Memoization is this pattern that is about remembering the outcome of previous executions of a function for a certain set of entry values of parameters. So here I'm creating a closure which does a simple plus operation on two numbers. So A plus B, but as you notice, I introduced sleep 1000, which is going to sleep for 1000 milliseconds. So as soon as I call plus 1 and 2, like here, the first time it's going to be executed, it's going to take 1 second to return the result. But because I memoized that closure, it's actually going to remember the outcome of previous execution. So the next time I call plus 1 and 2, it's going to return the result immediately because the return value of the previous execution has been cached in some recently used cache. If I use a different set of values, first invocation, it's going to take 1 second, and second invocation is going to return immediately. So that can be pretty useful. But be sure to put side effect-free code inside your closure, in the sense that if you return, let's say you would return new random as the return value of the closure. Obviously, if you use memoize, you will always return the same random value instead of getting a new random value each time you invoke the closure. So it's great for functions which are side effect-free, which always returns the same result for the same input values. There are some variants, like you can say, I want to memoize at least a certain number of values, or at most 10 values, or you can say, okay, between 10 and 20 values. And if you're afraid, well, if you're not using one of those variants, like memoize at most or between, don't be afraid of memory issues, because there are some soft, I never remember if it's soft keys and weak values or the reverse, so that when there's a garbage collection going on and when you're low on memory, it's going to reclaim those cached values. So it's quite safe to use. Some of you perhaps went to the presentation on the JSON API for Java EE. Anyone went there? Yeah, a few of you? Okay. So it's an interesting API. It's nice to see that coming to Java somehow as a standard. Although perhaps that would have been nice to have that in Java EE, not just for Java EE, but that's another story. So Groovy has got some built-in JSON support. For those knowing Groovy quite well, one of the nice things with Groovy is how you can handle XML content, how you can produce XML content, how you can produce and consume XML content. So it's very efficient in just one line of code. You can easily go through a whole XML graph and find just the values you're interested in, etc. A bit like XPath, if you will. And also for producing, thanks to our builders. So we wanted to provide the same kind of support for JSON as we had for XML. And that's what we did. So the URL is a bit shortened here. I didn't want to put the full-blown URL. When you use the REST API from GitHub, there's a JSON endpoint. So you can, for example, if you look at the commits on the Groovy repository on GitHub, you can have all the recent commits on the Groovy repository. And well, just one word before particularly talking about JSON, but Groovy adds new methods to the JDK, or you can even add your own methods to JDK classes, even final classes, thanks to the fact it's a dynamic language. And for example, we added getText method, which can be shortened to .text as a convention. In just one line, new URL, blah, 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 .text, you can retrieve, you can do an HTTP GET of a remote resource without having to use something like create a buffered reader over a URL input stream with open connection, etc., and then do a while loop to append all that stuff in a string builder or something like that. In just one line of code, you can easily get the content of a remote endpoint. So in the payload variable, I have a string representing the list of commits, a JSON string, of course. Then I'm instantiating the JSON slurper, and then I can call parse text to parse that JSON content. And then I have a document. That document is actually a structure of maps and lists, basically. So once you have a list of maps or maps of lists, etc. So a list is for JSON array, and a map is for the JSON objects. And then you can say doc.commit. It's going to find all the commit keys inside the document. And then you can say .message. It's going to find all the message attributes of those commit objects. And then for each of those messages, I'm going to print the message, the commit message, without having to define any kind of marshalling and marshalling logic or library or whatever. So it's that's because Groovy is a dynamic language that you can do things like that pretty easily, rather than having a pretty verbose API in Java. And so this is for parsing, but you can also easily create JSON content. So you create a JSON builder object, and then you have that builder notation, as we call that. JSON.person, I'm going to create a new JSON object with a person key. And I define a new object inside the curly braces with name as a key, Guillaume as a value, etc. And pets, Hector and Felix, is going to create a key pets and a JSON array containing 2 pets. And then I can call toString to print the JSON representation, and that's going to create the equivalent JSON content that you see here. Actually, it's not pre-printed by default, so it's everything on a single line. But if you want to have nice output, you can use that. It's a class of the Groovy JSON package called JSON output with a static method to pre-print your JSON. So we can just say pre-print, you pass the string, and it's going to output a new string, return a new string, which is pre-printed. So that's pretty useful for interacting with all those REST APIs, which now basically all support JSON payloads. A key aspect of Groovy, especially since Groovy 1.6, that was introduced, this AST transformation concept was introduced in Groovy 1.6. The AST stands for abstract syntax tree, so that's the internal representation, in-memory representation of a Groovy program before we actually generate bytecode, class bytecode. And the thing with AST transformation is that you have a chance to interact with the Groovy compiler. So you hook into the compilation process so that you can change things, like add a new method node inside the AST, so that afterwards you can create a method in the bytecode, in the real bytecode. In Groovy 1.8 we added lots of transformations, and I'll just cover a few of them. I'm going to cover just a few of them, like the log transformation. If you annotate a class with @log, it's going to create the logger and instantiate the logger field for you. And so it supports the different kind of logging libraries like Java util logging, commons logging, log4j, select4j. You can also create your own if you have your own logging strategy. And do you see, so first of all, so it injects a log field in your class, and you see that I can just say log.info, although I didn't define log anywhere, because there's a field which is injected automatically and transparently. And do you notice something else missing in how I'm using the logger? That's just to see if you're still...
Where did you select which one?
Sorry?
Where did you select which one?
So actually it's because of the, so how do you select which one? It's because here I used @log, but if you want to use commands logging, you would have used the @commands annotation. Okay? Now what's missing? Usually you wrap your logging statements with if log is debug enabled, blah, 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 or something like that. Okay? And actually the AST transformation wraps the log.info calls with the proper if around that. So you can save some further keystrokes by avoiding to wrapping all those things or forgetting wrapping those things. This transformation does that for you. So what's nice with the AST transformation is that sometimes we call that compile time metaprogramming, because that's about metaprogrammation, but it works at compile time. And for example, even if you use that class afterwards from within a Java class, the log field is there, and you can potentially use it. So that's quite powerful and works at compile time. Perhaps I'll mention that very quickly. Sometimes people, one of the nice use cases of Groovy is that you can easily integrate that in your Java application for further customizations, for user scripts, for various use cases, for business rules, for defining domain-specific languages that you want to integrate in your application, especially for the business rules. And sometimes that happened to one of my customers. Sometimes they run in their Java application, in their application servers, they run user code coming from somewhere, from their customers, etc. And if you want to be able to control what's going to be executed, for example, if someone contributes a script which is going to be run by your application server and application, and if it's doing some kind of while loop, for example, like that, it's going to loop for a while, and it's going to need lots of CPU, and it's not going to end and terminate. So what the add thread interrupt transformation is doing is that it's, notice how you can annotate an import, by the way. It's actually adding this hidden statement at the beginning of every block of code and every method, the start of every method body and the start of every closure body. It adds a call to see if that the current thread which is running, has it been interrupted from another thread. If that's the case, then I'm interrupting the flow here and throwing the interrupted exception, so that you can say, okay, this script ran way too long, now I can shut it down. Something that I'll mention afterwards is that you can hide, you can somehow inject such transform transparently, so that users don't have to put add thread interrupt themselves, because otherwise they wouldn't probably do a while true loop, which is empty anyway. So you can inject that, but that's for the sake of the example. So you can provide custom conditions, you can provide time conditions, run no more than 10 seconds, etc., depending on the annotation that you are using. So it's nice for integrating Groovy into your applications, especially when the code which is being run comes from somewhere else and you don't necessarily have control over that code. Some other handy features. Again, the compiler doing the job for you of implementing certain things, like default to-string implementation, which is a bit nicer than the default toString implementation in Java. So you just annotate with add toString your classes, and then you're going to have that person PT15 string, which is going to be returned when you do toString. And you can customize that with some options. But obviously, you can also still define your own toString method. That's probably, if you want really something very custom, you'd better use a toString method. But if you want to, for debugging purpose, etc., that's nice to have a default toString method, which is a bit more clever. Equals and hashcode. If you want to implement equals and hashcode, that's a bit of work. So here I have a coordinate class that I annotate with equals and hashcode. I create two coordinates with the same x and y values, and then I can assert that both values are the same. That's the same coordinates, and that the hashcode values are also the same. And tuple constructor. So in the previous example, you see how we use named arguments, coord x colon 20, comma y colon 5. That's named arguments. Actually, it's going to call the default constructor, then call each setter in turn. So it's going to call set x 20 and set y 5 after the constructor has been called. So in Groovy, often people use that, but especially in Java, we usually also create constructors which take those essential fields for your class. So I can say new person Marion 4 with the usual constructors taking fields as parameters, making the correlation between the parameters and the actual properties of your class. And you can actually, I wanted to also mention, I removed that slide, that we also have a transformation which is called add canonical, which takes toString, equals and hashcode, and tuple constructor transformations and mix them all so that you have classes which provide all these things. So you just annotate the class, the person with add canonical, and you've got for free all those transformations and all those new methods implemented for you by the compiler. That's quite powerful, and it'll, for those who knows Lombok, it'll remind you something. So we chat with the Lombok, our Lombok friends, and we've got some cross-pollination between our projects because that mechanism serves the same purpose in Java with Lombok and the AST transformations in Groovy. Another one, when you create exceptions, you have custom exceptions, extending exception. You have to create the constructors, the default constructors, and overriding the same constructors as you have in the exception class. And usually there are dumb constructors because you just call super and you pass the same parameters. So that's a lot of boilerplate code. There's a lot of boilerplate code in general in Java. And if you annotate your class with @inherit constructors, you inherit the constructors of the parent class, and you don't have to write that yourself. Okay, there are many other things, but I really want to spend some valuable time on Groovy 2.0. And, I have some older presentations on slideshare.net/GLAForge. That's where I usually put my presentation. I'll put that one soon online afterwards. So if you want to learn more about those older features, have a look at that. And, I forgot about that. I mentioned earlier that you can inject transformations transparently if you don't want to view the annotation. And that's why compilation customizers are for, so that you can inject some other transforms transparently. But, well, I'll just skip that. It's not really critical. But that's nice for integration. For example, in that example where I want to do some math expressions and I don't want to always see import static Java long math star in all of my Groovy expressions that I want to evaluate, I can inject that import transparently so that people don't have to prefix with math.py, math.cos, etc. Okay, so now let's move on to Groovy 2.0. There are three big themes. First of all, modularity in Groovy. So it's not quite the same scope as Jigsaw, for example, but well, we'll have a look at what it means. Then the Java 7 theme with the Project Coin syntax enhancements that came to Java 7. The invoke dynamic support, because Java 7, JDK 7 comes with a new bytecode instruction for facilitating the implementation of dynamic languages. And there's a third theme, which is a static theme in the sense that you can do the same kind of static type checking, or even in some cases better static type checking than Java itself, and as well as static compilation to generate the same kind of bytecode that the Java C compiler generates, so that you have a nice, Groovy being somehow a nice DSL for Java, to have the same speed of Java, etc. So, first theme, the modularity. The Groovy all jar containing everything, because Groovy is not just a language, but it's also a set of APIs. So it's a quite big jar with 6 megabytes, and not everybody needs everything. For example, in the Groovy APIs, you have a template engine. You have some builders for creating swing UIs, but if you're writing a servlet application, for example, you don't need all those swing UI things. There's so what we want to do is to let people being able to just pick up the parts they are interested in. So we split Groovy into smaller jars. So there's still an old jar so that you can not avoid changing your POM or Gradle dependencies. But we also have smaller jars so that you can pick up just what you want. And as part of that work, we need to be able to inject some methods, like all the extension methods that Groovy adds to the JDK. We needed a mechanism to be able to extend existing classes with new, enrich with new methods. So, and you'll see that it can be useful for you, not just for the modularity work that we did with Groovy, because you can extend JDK classes again at compile time, which is interesting, rather than dynamically at runtime. So there are quite a few new jars. So there's the core jar is still 3 megabytes, and which means that all those other APIs were about 3 megabytes in size. And we've got some dependencies between those modules. So for example, if you want to use, let's say, the Groovy templates module, it depends on Groovy, the XML template, because we also have an XML template engine. So that's why it depends on XML, etc. So there are some dependencies in our modules. And we can extend classes with our own extension methods. And for that, you'll need a descriptor that I'll mention in a couple of slides, and a class defining, or several classes, defining extension methods. For example, if you want to add a new method on string, you're going to define a class containing a static method. By default, that's the convention. It's a static method. The name of the method is going to be introduces. The first parameter is actually the instance string on which I'm going to work. And then the remaining parameters are the actual parameters that you pass to the introduce call. So here I'm going to return hi, blah, blah, blah. And for example, the last line about the usage, you say Guillaume dot introduces, and the Cedric parameter, that's my colleague on the Groovy project, is going to be put in the string name parameter. And the self is going to contain the string Guillaume. So that's a convention. That's for instance method, but you can also, so that's for those who knows Groovy categories, that's the same kind of structure, the same kind of conventions, a class with static methods, and the first parameter being the actual instance on which we're working on. And you can also do the same for static methods, not just instance methods. For example, if you want to create a static hi method on string, this is again the same structure as before. The first parameter is actually, you don't care about the actual instance. The important part is the fact that it's a string class, basically. The type of that variable is string. And then you're able to say string.hi to return the string hi. And then you have to wire that in a descriptor. So that's just basically a properties file that you put in that special location. You can give a name and a version to your module, and you can define a list of extension classes, for instance, methods, and a list of static of classes for static methods. So that's how you describe that. So all our modules contain such a descriptor with some common extensions. So that's and also, if ever I forget to mention that afterwards, this is working also for the static type checking feature as well as the static compilation. So you can add, do the same kind of metaprogramming, runtime metaprogramming that you do with Groovy usually. It's also working in a static context, whether it's for type checking or for static compilation. So the second aspect, Java 7. So we added the project coin enhancements, like the binary literal notation. So you can define numbers with ones and zeros, with the 0b prefix. We also added the underscores in your number literal, so that you can separate like the 4 digits of credit cards, the groups of 8 bits, groups of 4 bytes, etc. We also have the multi-catch notation, where you can coach several annotations, several exceptions, sorry, in the same catch block. So you say exception 1, pipe, exception 2, etc. So this is just like Java 7 project coin enhancements. There's nothing special there. And in Groovy 2.0, we introduced the support for JDK 7's invoke dynamic. So that's a new bytecode instruction that you can use to speed up dynamic method invocations. So we've got a special jar for that, so that if you're not running on JDK 7, we don't require JDK 7 because Groovy 2.0 still works with Java 5. Java 5 being the minimal requirements. And what's nice is that it brings some better runtime performance, and in the long run it will also allow us to get rid of some of our code that we've been using for improving the speed of Groovy. So, well, it's kind of hidden to the users because it's not something you see when you write Groovy code, but if you use the invoke dynamic jar, the Groovy jar with the invoke dynamic support, you should get better performance with Groovy if you're lucky to run JDK 7 in production, which is not yet that common. Who's using JDK 7 in production? Okay, if you in JDK 6? Yeah, that's the majority. So if you want better performance with JDK 6, and when you use Groovy, you can use the static compilation feature that I'm going to mention in a moment, for example. Let's talk about that. Static type checking, static compilation. So the idea was to make for the static type checking part, the idea was to make the Groovy compiler more grumpy, like the grumpy dwarf. And throw compilation errors compilation errors at compile time, obviously, rather than having errors at runtime. So usually you don't get errors at runtime because usually you test your stuff, you run your code somehow at least once before putting things in production. But if you want to get some early feedback from the compiler when you do things like typos for method names or that kind of things, you can enable the static type checking for your classes. And it does a few other things. So let's say here it's a script. I have a script with a method. And inside my test method, I'm going to call the method, but I make some typos. And also I have a local variable called name. And then again, when I print in that name variable, I have some obvious typos again. And instead of getting errors at runtime, if you run that script, you're going to get compilation errors, just like you would with the Java C compiler. And the annotation, so this is just the test method, which is statically type checked, but you can put that annotation at the class level or at the method level. So perhaps you want the whole class to be statically type checked, or you might just want one particular method to be type checked. What this feature is doing, if you're doing some wrong assignments, like you want to assign an object into a primitive value or some class into another class with which it's not compatible, or if you want to say, like you have an array of strings and you want to retrieve an element of an array and put that inside here in my example, an int variable, or if you want to append a string to an int that doesn't mean anything, and all those errors are going to be caught at compilation time. Also, if you're making mistakes with your return values, in this example I have a method which returns an int, and I say if true I return a string, otherwise return an int, but the compiler will complain because string is not an int, of course. And if you want, and there are some cases where it doesn't complain. If you look at the last statement, SB, left shift high, left shift name, this is returning a string builder at each. It's the equivalent of SB append, basically, because I'm using operator of loading here. And it's returning the string builder, but Groovy has this convention that if your method returns a string, it's going to call toString on the return value if it's not a string already. So those things which are common practice in Groovy, the compiler won't complain. So that it's just a matter of adding the annotation, but still write the same kind of code, basically, so that you don't have to change the code. It's just statically typed, but you don't have to change the way you usually write Groovy code. It also supports type inference. For example, here I have a G-string where I print a name, and I have the interpolated value with the dollar curly brace, and it won't complain because to uppercase is a method on the string, so it's obviously understanding that. The trim method, which is a method from the GDK, the Groovy Development Kit, it understands that as well, so it's not going to complain. And well, it's able to destructure the values inside the array also. So it's understanding, so it knows at every step what's the value of the variable or the thing on which you're working on. Thanks to type inference. There are some cases where you want to mix statically type checked code and dynamic, classic dynamic code. For example, when you use Groovy Builder, it's typically a very dynamic feature, and it's not something that you can type check with the compiler. So you can have one method which is type checked, and the other which still has the same dynamic features. So you can decide what's dynamic, what's statically type checked by just deciding where you want to put the annotation, basically. For things like instance of, when you do instance of on a variable, and you've got different cases because you've got a val object, you don't know what's the type of val. When you do val instance of string, in Java you have to cast val or create a temporary variable, etc. But you need those casts. And thanks again to some logic and some type inference, inside the if val instance of string block, it knows that val is actually a string, so I'm allowed to call the toUppercase method from string. And also later on in the second block, val is a number, so I can call int value on the number, and it also understands, so no need for cast. So again, some boilerplate code which is removed compared to Java. And it also understands the operator of loading going on thanks to the Groovy Development Kit. So it's quite clever, basically. And speaking of type inference again, there's what we call lowest upper bound, because the type inference that we're doing is quite clever in the sense that we are able to, how shall I say that, to have a better understanding of the types we're working with. For example, what would be the type, the inferred type of square bracket 1234, 3.14? So it's an integer and a big decimal. 3.14 is a big decimal. What's the inferred type of that collection, in your opinion? Anyone tries to guess? What is it? A list of number, yeah. Actually, it's a bit more than a list of number. because the thing is that integers and big decimals are actually also comparable, but number is not comparable. So the inferred type is a list of something which is a number and a comparable. And it's not something that you can write in Java with the Java type system, but what I want to say here is that the inferred type is a bit more fine-grained than what Java allows us to write, basically. So it's a list of number and comparable. So with some more lube, everything is smoother, obviously. And another aspect of type inference is what we call flow typing, because we look at the flow of execution. And for example, here we have a variable in which we put an int, and then we put a string inside that variable. When we call toInteger, because we know it's a string, we can call the toInteger method from the Groovy development kit. And afterwards, we put back, again, a number. And here you would get a compilation error because to uppercase is not valid on a number. So it's able to follow the different. So it's not actually a good practice to change the value, the type of a variable. But because of dynamic typing here, people can do that, although it's not usually something that I advise to do. Some gotchas. So type checking isn't changing the behavior. Behind the scenes, it's always the same kind of dynamic code which is going to run. So do not confuse that with static compilation. Most dynamic features cannot be type checked, especially things like meta-class changes, like the builders, etc. So this cannot be type checked by the compiler because it really depends on what's happening at runtime. However, all the things like the AST transformations, like the extension methods from the extension modules that I presented earlier, all those things, because it's about compile time metaprogramming, although it's pretty dynamic, this is obviously supported with static type checking and, of course, static compilation. So just an example, for those who use Grails, you quite often use the exponent meta-class to add new methods to types. And that kind of code is not allowed because meta-class is a dynamic property, so it's not supported. And it would complain as well with the foo method, which is not recognized because it's only added at runtime. And there's actually one little gotcha, because I want to be honest with you, where you have to actually change your code a little bit. But it's something that we're working on to avoid having to change the code that you write. For example, if you've got a list here, you can infer that it's a list of string, but imagine that the list is coming from elsewhere. The static type checker doesn't know that toUppercase can be called on the current instance, the current value, the current item of the collection. So you have to be a bit more explicit and say string it, so that the compiler, the static type checker, knows about that. But we are working on a solution to give more meta information to our Groovy development kit extensions so that you don't have to do that kind of things. Well, I think I might probably skip that. It's again about the flow typing capability. When you have some variables, local variables, which are shared within the body of a closure, you can't really know if the closure is called. For example, if you've got a random value, so I put a string into my variable, and then perhaps I'm going to call that closure depending on a random value, which is a runtime aspect. Perhaps the variable is going to contain a date, or perhaps it's going to be a string. So for those things, the compiler will complain because the variable is shared, and perhaps you assign something in that variable, but there's no way the compiler knows at compile time that it's a string or is it a date. So it's going to complain here because it cannot be sure that it's a string, so it cannot call toUppercase. But for the case where you have something like class A and class B, which extends A, since you know that, so in the test method, I'm assigning an instance of A, then the closure might put an instance of B, so B is also an A, so you can call all the methods of A because that's the common lowest upper bound of those two classes. So it's going to just work. So just be aware of that there are some cases where you might have some surprises, and the static type checker might complain because there are some aspects which are typically runtime aspects that cannot be statically type checked. So, well, it's basically the advanced cases. And I'll finish with static compilation. Given that you can statically type check your Groovy code and have the same kind of compiler feedback as with the JavaC compiler, what about compiling it statically and generating the same kind of bytecode that the JavaC compiler generates? For those who are not lucky to be running JDK 7 in production, to benefit from the JDK 7 invoke dynamic instruction to get some performance improvements, you can still get quite awesome performance improvements by using static compilation. For those parts of your code base, because static compilation relies on static type checking, for all those non-highly dynamic parts of your application, you can say at compile static to say, okay, I want this method or I want this class to be statically compiled to generate the same bytecode as JavaC to get the same performance, or more or less the same performance as Java. So you gain type safety thanks to the static type checking aspect. You've got faster code close to Java. And also it's interesting for those who are creating libraries and frameworks with Groovy, the fact that you can do meta-programming at runtime, you can change the behavior of existing methods on some particular types. And sometimes people could actually impact your framework code by changing the behavior of a certain method that you are using in your library. So that's what we call monkey patching, or the Rubyist call monkey patching. And if you compile things statically, it's not going through the Groovy meta-object protocol, which is the runtime, which is the dynamic heart of the Groovy runtime. And also another, benefit is also that you can get smaller bytecode for, if that really matters for you. And how do you do that? Before some disadvantages. So just like with static type checking, it disables certain dynamic aspects. So like the builders, like the categories, etc., it cannot be supported. But all the compile time, AST transformations, extension methods, etc., are supported. So you can still do dynamic meta-programming, but that is understood at compilation time. And there are one case where the behavior, because it's not the same bytecode that we generate, where the behavior might change slightly. This is the case with overloaded methods, what we call the multiple dispatch. So you might have some cases with overloaded methods where it might change in terms of behavior because dynamically Groovy decides to call this particular method because of the type of the parameters at runtime. But here, since it's something that is happening at compile time, it does a best guess, thanks to type inference, to call the right method. But usually, in most cases, you're not going to be affected, but be aware of that little gotcha. And if you want to mix things which are statically compiled and dynamically compiled, just like the previous example with add type checked, with the add compiled static annotation, you can put it on one method because you want just that method to be statically compiled. And if you want to use dynamic feature, don't annotate the method containing the dynamic features with add compiled static. So again, just like type checked, you can put the annotation on the method or on the class. And there's also, something I don't mention here, but there's also, for example, if you put the compiled static annotation on the class, you can use add compiled static and type checking .skip to say, okay, I just want to skip one method so that it's not statically compiled. So it's more granular. And what about performance? So I did some experiments with some small micro benchmarks. So usually, if you've got a performance problem, be sure, before showing you the example, if you've got a problem of performance, you'd better measure before trying to guess, so that because sometimes people just look at some silly micro benchmark published on the web somewhere. Oh, Groovy looks slow. Yeah, but perhaps that's a case where it's slow for some reason, for some good reasons. So don't evaluate a language just because you've seen some micro benchmarks, but because you actually measured performance on all the performance characteristics of your application. Well, anyway, that little warning mentioned. I did a measurement with 3 different versions of Groovy. Groovy 1.7 without any kind of optimizations beyond the call side caching optimizations that we have since Groovy 1.6. In Groovy 1.8 we introduced some primitive type optimization, so that when you use primitive types, we do the right bytecode instructions to use the I-add bytecode instruction to avoid boxing and so on. And I also did the same stuff with static compilation. So I took 3 different micro benchmarks, like the Fibonacci series, like the calculation of pi with the quadrature algorithm, and binary trees, that's an algorithm for doing some search in binary trees. And I measured with different... what's interesting with those micro benchmarks was that it typically shows where Groovy had the worst case performance, basically. In most applications, business applications I've seen, it's never been a problem. But in those micro benchmarks typically show where Groovy was bad in terms of performance, especially in primitive type calculations and lots of recursive method calls and that kind of stuff. So if you look at the time it takes in Java, and you look at the very last line of the table, you'll see that in some cases Groovy could be 20 times slower than Java or something like that, or more than that, okay? 30 times and more. So Groovy 1.7 in those worst case scenarios was quite bad. With Groovy 1.8, we added some primitive optimizations so that we generate the same kind of bytecode as Java-C just for the primitive type calculation. So you already got some pretty good figures. And then with static compilation, we get pretty much the same performance as with Java. So except in the binary trees example, but we're working on that. So it's just like 20, perhaps something like 20% slower than Java. But that's the kind of performance that you can get. You can get Groovy to be as fast or almost as fast as Java. Okay, so for those who thought that Groovy, because it's a dynamic language, it's slow, that's not really the case. Okay, that's pretty much it. So the big themes for Groovy 2.0 were the modularity aspect, all the JDK 7, Java 7 enhancements with the project coin syntax enhancements and the invoke dynamic support, and the static aspect with static type checking and static compilation. So thanks a lot for your attention, and I have only 3 minutes for taking a couple of questions. So any questions in the audience? In the back over there? Yeah, that's you.
About the future?
Yeah, about the future? Yeah. So I have just one slide I added just in case someone asked the question. So we're going to release Groovy 2.1 at the end of the year. Initially, that was the end of this month, but that's probably going to be at the beginning of December or mid-December. We are adding some further support for enabling better tooling, code completion, etc., as well as improving the static type checking capabilities for those DSLs like in Gradle or in Grails, etc., where you have methods that take closure as parameters. And you know that thanks to the closure delegation strategy, all the method calls inside the body of that closures are delegated to some object. We're able to do some more type inference and code completion in IDs, etc. So we continue to improve the tooling aspects and the static type checking aspects. There were some parts of Groovy which were not using, for if you use the invoke dynamic support in Groovy 2.0, not everything was using invoke dynamic support. So we totally complete the invoke dynamic support in Groovy 2.1. Plus some other things like the ability to define custom static type checking. And that means that you'll be able to have some finer grain type checking that you could have with Java, for example. So it's quite advanced. So you can define your own static type checking for your own DSLs, etc. And also, it's not yet decided if we're going to do that, but like the @canonical annotation, you may be able to define your own meta annotation to define a set of transformations that you want to apply to your classes and scripts. And beyond that, Groovy 3 for 2013, we're working on a new meta-object protocol that we've been promising for years. The Java 8 Lambda support, because we have closures, but, well, we'll have to support Java 8 Lambdas as well, so we're going to work on that. And Groovy 4, the sole big item for now for Groovy 4, but we still have time to add many more features or ideas. It's using a more recent grammar with modular 4, so we're going to rewrite the grammar. Still the same syntax, obviously, but well, that's it. Perhaps just one last question. No more question? Okay, that's cool. So thanks a lot for your attention.